Converting a normal distribution into the standard normal z. This particular step in solving for the probability is very important since most of the applications in real life are not given by z number. For example, if all the units and terms are in terms of weight, mass, length, or whatever quantity, then those quantities should be converted first into z number before we can solve for its probability distribution. We can do this by using the equation that z number is equivalent to the number x minus the mean divided by the standard deviation. Take this example. Suppose a population is normally distributed with a mean of 24.6 and a standard deviation of 1.3. What percent of the data will lie between 25.3 and 26.8? As you can see, all of the givens are not in terms of z values. So the first step we should do is to convert these values first into z numbers. And we have 0.5384615 for 25.3, and we have 1.69230077 for 26.8. In illustration, we still have a bell-shaped normal curve, but the values of the variable will change. Take the number 24.6 for example. You can see that this number is in the middle because this is actually the mean. So if we convert this 24.6 into a z number, this will give us a z value of 0 because the z value in the middle of the normal curve is 0. And now we are tasked to find the percent of the data that will lie between 25.3 and 26.8. So 25.3 is approximately 0.54 of the z values. So let's just assume that the z value is here and the 1.69 is here. To solve for the area in this region, we have to find the value of the area left of 26.8 for x or 1.69 for z and subtract it with the value of 25.3 for x and 0.54 of z. Using the table, that is just 0.9545 minus 0.7054 or equivalent to 0.2491. Convert this decimal into a percentage. Approximately, we have 24.9% of the data will lie between 25.3 and 26.8. This kind of applications are very useful in real life problems. And we will be solving few of that in this video. For another example, we have the mean weight of a box of cereal filled by a machine is 16 ounces with a standard deviation of 0.3 ounce. If the weights of all the boxes filled by the machine are normally distributed, what percent of the boxes will weigh the following amounts? And since all of the given values are in terms of ounces and not in terms of z values, we have to convert them first. So for letter A, we have 15.5 ounces. This is equivalent to 15.5 minus the mean of 16 divided by the standard deviation of 0.3. and that is negative 1.67. So to get the area left of it, we have to refer to the table. That's negative 1.67 right here is equivalent to 0.0475. So the probability that the value of z is less than negative 1.67 is again equivalent to 0.0475. Converting this value into a percentage by multiplying it with 100, this will be converted into 4.75%. That means 4.75% of the box will have a weight of less than 15.5 ounces. For letter B, we have to find the percentage of the boxes that will weigh between 15.8 and 16.2. The first step, again, is to convert first these values into z value. That's 15.8 minus 16 divided by 0.3. It's negative 0.67, while the 16.2 is positive 0.67. With this, we have to find the probability of the z value from negative 0.67 to positive 0.67. From the table, positive 0.67 is equivalent to that's 0.7486 minus negative 0.67 is 0.2514 and this is equivalent to 0.4972. Or this is equivalent to 49.72%. That means 49.72% of all the boxes being manufactured will weigh between 15.8 and 16.2 ounces. Now let's solve this another example. The amount of time required to assemble a component on a factory assembly line is normally distributed with a mean of 3.1 minutes and a standard deviation of 0.6 minutes. Find the probability that a randomly selected employee will take the given amount of time to assemble the component. A, more than 4 minutes, and B, between 2 and 2.5 minutes. So let's convert first the value of 4 minutes. 4 minus 3.1 divided by 0.6. 1.5. So for letter A, we are actually looking for the area right of the z 1.5 because of this term right here. That's more. So in the curve, let's say this is the z is equal to 1.5. We are actually looking for this area. And the area to the left is the one given in the table. So what we're going to do is to subtract that area from 1 to get the value of the area above 1.5z. From the table, 1.5 is equivalent to 0.9332. So the probability that z is greater than 1.5 is equivalent to 1 minus 0.9332. And this is equivalent to 0.0668 or 6.68%. So that is the probability that a selected employee will manufacture a component for more than 4 minutes. For letter B, we have to convert the 2 and 2.5 minutes into z values. This is negative 1.83. And this is negative 1. So the probability that the value of z is from negative 1.83 to negative 1 is equivalent to the area left of negative 1 minus the area left of negative 1.83. So negative 1 is 0.1587 minus negative 1.83 that's 0.0336. That is equivalent to 0.1251 or 12.51%.